I'm really excited to talk about bridging this gap between AI research and policy. A little bit shorter of a title than I initially submitted, and hopefully I'll be able to cover a good amount of content that I put in the abstract. Okay, so as all of us know, AI has moved from the lab into our homes and institutions, and there are a lot of consequences. So here I'm just sort of like listing a bunch of impacts of AI. AI intervenes on our private sphere. We see this through how social media mediates our personal relationships. It has profound economic impact. We see that in the transformation of our workforce. It affects our rights and livelihoods, through a right to privacy and the use of employment algorithms. Harms consumers. We see this with instances of self-harm as well as antitrust law. It poses various societal risks, including propagating systemic biases, and it also raises various existential questions around, for example, AGI. So when you talk about policy, people often pull up something that looks something like this, where you have AI's growth, adoption, and impact in the top left, and that inevitably causes some unintended harms and externalities. And I think basically no one would deny this at this point. And we typically try to accommodate for that, or not accommodate, but kind of counter that through regulation and litigation. And I think what increasingly is agreed upon is this last bidirectional arrow here, which is that regulation and litigation can actually facilitate the growth of AI, its adoption, its impact, because without public trust, we have kind of limited adoption. Okay, so before I get into kind of two projects, I really wanted to just flash this up because when I talk about AI policy, I think some folks, usually have some sense of what they think of when they think of AI policy, and this kind of overwhelming list is meant to say it's quite vast. And so we can think of some early work on privacy, discrimination, risk management, sort of inspired by the EU AI Act as well as Biden's EO, various works on AI auditing and evaluation. Recently, a bit of shift to actually promoting AI innovation, as well as considering issues of national security, geopolitics with China, chip export controls, and so on. Most of you probably know of various issues that are rising in intellectual property and copyright, as well as personality rights, for example, name, image, and likeness issues. There are various questions around antitrust, manipulative and unfair practices, protections for whistleblowers, questions around mental health and self-harm, CCM, child sexual abuse material, robo-scams, social media, democracy and civic discourse, and many, many more. So this is really this is meant to be a kind of overwhelming list that says this space is vast, and if there are components of this that you're interested in, you might, consider thinking about AI policy, sort of the policy angle to these. Okay, the thing is, most of us in this room, we're not policymakers, including myself, and so how can research contribute to policymaking? And this was kind of really a central question for me during my PhD, trying to navigate the space, but coming with two advisors who were definitely not policymakers and not really plugged into policy and law, and trying to navigate and say, where can I actually have some impact? And so something that I'm definitely still learning and exploring, and I'm sure many of you in this room actually have more experience than I do. And so if I were to summarize maybe some of the things that I've gathered, I would just point to these 3 E's. I think the ways that we can often contribute our expertise, like lending our time. This is often slightly invisible work that happens in research, but staffers might ask you, hey, can you read over this bill and give me your comments, or we got this opposition letter. Tell me what you think, is this argument actually BS that some opposition company is providing them? There's also the sort of engineering component, and I'm going to focus mostly on these last two today. Engineering component, and here I'll talk about how engineering can actually help reduce some of the gaps that we see in AI governance, especially because we are dealing with the technology. And we'll do this by looking at audits under resource and access constraints. And the final E is how evidence itself can just build consensus by sort of grounding conversations and therefore spur action. And we'll look at a project that sort of gets at this with tracking relationships in the AI industry. Okay, so happy to take questions, by the way, throughout. Feel free to interrupt me. I'll try to scan the room every once in a while. Any questions so far? All right, great. So let's start with maybe that middle one, how engineering can help reduce gaps in AI governance. And this is largely based off of this paper with folks at Stanford, Audits Under Resource Data and Access Constraints, Scaling Laws for LDAs. And it's with my wonderful colleagues, Salil, Zaina, Ananya, Percy, and Dan. Okay, so what is the motivation? The motivation is actually known to quite a few folks in this room who have written the related works that I'll put up in a few slides. But our legal system operates or relies on the production of persuasive evidence. And we see this often in sort of court cases. But gathering sufficient evidence to meet the necessary standards in AI-related cases is often challenging. And two of my collaborators have done a phenomenal legal analysis to illustrate this. This fact, the importance of evidence, is kind of well known. I would argue that like a lot of the discussions on AI evaluation and auditing are basically building on this concept that we need evidence for enforcement of AI laws. And then sort of separately, and what we'll build on today, is that I would argue it's even more important in things like private litigation. So especially in the current state that we're in, which is sort of the absence or lack of legislative and administrative action, we often turn to private litigation to kind of fill in some of the gaps. Okay, so how can we look at this more closely? Let's instantiate it by looking at a specific case study. So let's look at Title VII. And this is going to be the longer portion of my talk, so I'm going to give you a TLDR in case you you can zone out for the next 30 minutes or so. And the TLDR is one way the law assesses if a decision rule is discriminatory is whether there are less discriminatory alternatives, also known as LDAs. In the context of AI, producing an LDA is pretty daunting, right? Like plaintiffs lack the compute, model access, data access, and expertise to necessarily produce one. And from an engineering/mathematical point of view, what we do is we derive a closed form upper bound for loss, fairness, Pareto frontiers. And we'll show how this actually maps to effectively a scaling law that allows you to infer something about LDAs in a small data, small model regime and extrapolate to what that means for LDAs in a large data, large model regime. Okay, cool. All right, so brief intro to Title VII, which was our motivation or like the lens through which we were looking at LDAs, although you can also think of LDAs through the lens of like the Fair Lending Act and so on. So Title VII, which many of you know, of the US Civil Rights Act prohibits employment discrimination based on race, color, religion, sex, and national origin. And it's very complex. We're going to scope to the disparate impact doctrine, and we're going to go through like the 3 steps in litigation. And I'm sure this is very, very well known for many of you, but the 3 steps go: the plaintiff first bears the burden of proof. They must first establish what is known as disparate impact. And this typically involves showing some notion of statistical disparity on the basis of one of those sensitive attributes at the top. Okay, quantifying disparate impact is the subject of like many years of research underlying this entire workshop. It is not the focus of today. What happens next? Well, if you successfully show disparate impact, the defendant can use what is known as the business necessity defense, which is effectively kind of an argument around like this statistical disparity that you're observing is a sort of inevitable fact that falls out of us moving towards our business purposes. Okay, and then the third and final step, where the burden of proof falls on the plaintiff, is that they can then show that there is a less discriminatory alternative. And this is the focus of today. What is an LDA? An LDA is effectively some sort of notion of an equally high-performing, that itself is a little bit fuzzy, but less discriminatory option that can be found with like reasonable or good faith effort. And if you think about what this means for AI, I would argue that this is quite daunting in AI-related cases, right? A straightforward interpretation is that the plaintiff must produce, so provide an AI model that performs just as well but is less discriminatory. And really to drive the point home, why is this challenging? There are a few limitations that people often face as plaintiffs. One is limited model access. Companies are very, very, very closely guarding their models. If you want access, they'll say, sorry, it's a trade secret. They will use a similar argument, and they might even tag on user privacy if you ask for access to training data. And finally, you as a plaintiff typically have way fewer resources than an AI developer or deployer has. So, as a plaintiff, you can't train comparative models from scratch or necessarily like tinker with the current model and like look at the neighborhood of the current model. So like if we're trying to formalize this a little bit, and I'll kind of cast it as a technical problem in a few slides with the figure, what we effectively do in this paper is we're going to have some notion of performance and some notion of fairness. Now in this paper, we're going to pick binary cross-entropy loss as our notion of performance, or the opposite of performance. And for fairness, the fairness gap, we're going to use the difference in selection rates, or demographic parity. We're going to then say that the AI developer, they have some like large compute budget B. The plaintiff, on the other hand, has some small compute budget B minus, and also some small data D minus. The plaintiff might know the approximate model family, like just simply transformers, but like not necessarily anything further. And the goal of the plaintiff is to determine if an LDA, if given the budget B, so like some notion of like what the AI developer would have been able to achieve, exists, even though the plaintiff themselves only has compute B minus and data D minus. I'll leave this up for a second and see if there are any questions. Is this clear? Yes?
Clarifying question. Do they have black box access to the model? Like they can call the model they're auditing?
In our scenario, I don't think you need black box access. You needed black box access in the like first two steps to assess disparate impact and to assess like some notion of business necessity. But for ours, we're going to actually kind of do a workaround. Thanks for the question. Okay. Oh.
Sorry, just very quick. Is it the same model family?
Yes, it should. So the question was, is it the same model family?
Does the LDA have to be in the same model family?
Thanks. It should be from the same model family approximately, but I think because we're relying on scaling laws, and roughly speaking, folks have shown that it's not incredibly sensitive to your architecture as long as you're like roughly within the same model family. Some scaling laws usually apply. We think that that's like approximately okay. Okay, all right, so ton of related work. You'll see some familiar names here. Back in 2024, Black, Kopke, Kim, Barocas, and Su take this position arguing for a duty of reasonable searches for LDAs. They basically kind of build on this concept of there exists model multiplicity, and that also means that in some sense, saying there exists an LGA is like kind of trivial, and so what instead we need is some sort of reasonableness of how much effort they put into searching. So showing evidence search and other details. Gillis, Merceau, and Ustin cast the search for an LDA over linear classifiers as a discrete optimization problem, which is helpful because it shows sort of hardness, but it also provides paths for like relaxation and solutions moving forward. And their goal is to produce this framework where like either you give an LDA or you refute that one exists. Laufer, Raghavan, and Barocas catalog issues that arise when you actually define LDAs. So I think they take some similar positions to Black et al. And they also show that like searching for LDAs is very difficult, and so they cast it as this other computationally hard problem, showing it's NP complete. This past year, in 2025, Hayes, Laufer, Barocas, and Raghavan ask what constitutes a good faith effort. Again, it's like a slightly different setting. You're not the plaintiff, you are the model developer. And so what constitutes a good faith effort when you search for an LDA, and they provide this sort of like optimal stopping algorithm. If you sort of fix the training procedure and you search over the randomness induced overtraining. Okay, so if there are questions later, I'm happy to return to like how ours fits into this related work. Okay, so the very first insight that we build on is maybe finding an LDA is really hard. So why don't we instead try to show that one exists? Maybe this will give us a slightly easier problem. And the first thing that we do is we say, okay, well, to reduce disparate impact, the employer is basically arguing to reduce disparate impact, we must sacrifice performance. And so the claim is something like the AI system is sufficiently close to Pareto frontier, and that sufficiently close is a detail that has to do with reasonableness and good faith effort that I'm going to slightly abstract away for this talk, just so that we can like make sure we understand kind of high level what's happening. Okay, so maybe something like this is a figure you should keep in your mind. Step 1 of the disparate impact sort of procedure says that we evaluate a statistical disparity at some point. That's kind of like establishing the fairness gap on the x-axis. And the step 2, which is looking at business necessity and performance, is kind of establishing the y-coordinate on this loss axis. So loss, fairness gap, we're trying to move downwards and to the left. And so let's say like after step 1 and step 2, we know where the AI system falls on this plane, and it falls there at the black x. Now we don't know where the Pareto frontier falls. If the Pareto frontier is this orange curve over here, then basically, to reduce disparate impact, you would necessarily need to increase loss. If we agree that this is an acceptable notion of loss and this is an acceptable level of loss, then no LDA exists. But if the actual Pareto frontier falls a little bit further into the left, down into the left, and is the red curve, then there's room for potential improvement, not only in terms of fairness, but also in terms of performance. Okay. All right, so what is this transformation or like view of this problem through Pareto frontiers get us? It allows us to go without model access, right? And the reason it allows us to do this is like, sometimes the way that we look for an LDA is we like start at the system and we kind of like perturb it in some way and we look in its neighborhood. But Pareto frontiers as a construct are like more model agnostic. They're actually saying, okay, well maybe we have the same budget and approximately the same model family, but otherwise it's a sort of model agnostic artifact that we're dealing with here. So this is the first step, but some of you probably will see a problem. But I just want to make sure that this is clear. We are taking this problem of like finding an LDA and casting it to a search for existence, and doing that by saying, let's find where the Pareto frontier falls. Yes?
To say that they should use the other thing if it exists, and if it's hard to find, maybe hard to find for them as well, right?
Yeah, I think that we'll need probably a variety of tools, but I think I'll come back to this a little bit later of like, there's some distance that may be reasonable to be from the Pareto frontier, and you can potentially back that out using our method with a little bit of like bootstrapping. Thanks for the question. Okay, all right, so that's helpful, but there's a problem. And some of you probably see this. And the reason why there's a problem is that typical ways of finding where the Pareto frontier falls are actually more expensive than finding an LDA, right? Like if you were able to find the Pareto frontiers down here, then you already know that like that's an LDA to like that guy. Okay, so the whole goal was to address the resource gap, not make this more computationally difficult. So what are we going to do? And our solution is what we call a scaling law for the Pareto frontier. And if I were to like map out our problem really easily, effectively the procedure looks like this. Step 1, you fit a frontier given a small compute budget, so small model, small data. And you extrapolate the frontier for the large compute budget B that the model developer actually has. Our main result is a theoretical scaling law that tells us how to extrapolate, right? Like you can start with the orange, but you're like, okay, where does the red actually go? Okay, so to get a little into the math, and I'll probably go slightly quickly through this, but I'm happy to like get into more detail if folks are interested. You mostly don't need to know everything on this slide for you to understand the main result. But we start with like a sort of classical setting where you have X your covariates. It can be unstructured inputs. It doesn't need to be like a fixed feature vector, a feature vector of fixed size. You have your sensitive attribute, and you have your outcome random variables. A is drawn Bernoulli from a Bernoulli distribution, and we say there sort of exists a subset of indices X such that XS is independent of A. Now this is actually like slightly relaxable. You can kind of do transformations on X and on A to make this happen, simplifying for clarity. And then you have some assumption that your model belongs to a model class calligraphic F. Okay, so how do we assume the data generating process for Y looks like? Y condition on X and A is basically a function of G operating on the features that are independent of A, and then this sort of like funky looking minus zeta A over here, where G is actually allowed to be anything as long as it's measurable. And I would argue that this is like pretty general because effectively you want something Bernoulli. Sigmoid gets you pretty far. G is flexible. This I'm oversimplifying, but this basically means every feature or transformation of features that is like not dependent on, that is independent of A. And then because A is binary, this just means that this is either minus zeta for one group or 0 for another group. And that just means that like there is some shift, and if zeta is 0, then there's no shift. Otherwise, there's some shift that comes from that minus zeta A for one group compared to another. Okay. All right, so what is our main result? Our main result is this. It looks really complicated. I will cover up part of it in like 2 seconds. But just what's happening on the left-hand side is this is loss. That was our y-axis. Over here, you have an expression of delta. So basically, all that's happening is this is a function of the fairness gap. So we have loss as a function of the fairness gap, delta. And the only important thing to notice here is that there are 7 constants. So there's 7 constants. And what I mean by constants, by the way, is that these depend on your distribution. They depend on P, but they're constants in scaling. So they don't depend on how large your model is or how large your data is. Now, that means that this is a scaling law, right? So it means that step 1, if we return to our previous like very simple procedure, is that you fit C1 through C7 using a small compute budget, so small models, small data. So you're just like fitting that equation up there. And step 2 is then you plug in the n and the d and the b correctly, and you might have to do a minimization over it correctly such that you can then extrapolate where the red curve falls. Okay, this is basically the main contribution at the end of the story, so I want to make sure that this makes sense. Yeah, go ahead. Maybe a mic.
Yeah, thanks. I'm trying to relate this to sort of, I guess, the intuitive concern that someone with a small number of parameters might have, that the company that they're, is the defendant in this lawsuit has access to a big model, and that maybe their loss is dependent on, some emergent property. Obviously, it's controversial whether there are any emergent properties, but that their loss, to get any reasonable loss, depends on being able to do multi-state reasoning or have a theory of mind of the customer, or something that only happens after X billion parameters, and I can't afford to train a model with X billion parameters, and therefore there's like a genuine discontinuity here that's going to not follow your functional form. Like how do we know that isn't going on for the particular property that this company is using? Yeah, that makes sense. It's a good question. I don't have a clean answer for you. I think if there are there's sort of a discontinuity here where you get a really big jump. It is potentially hard to just take this approach in any way altogether. One possible argument is that this will give you a conservative estimate of the Pareto frontier, right? So you're arguing that maybe the true extrapolation is not orange to red, but orange to something that goes even farther down and to the left. And so I think that one way this still kind of works is you are getting a conservative version of it potentially, and as long as if you're still able to prove that an LDA exists even under the conservative version, then you still have a potentially even more stronger argument. Of course, if it falls, that requires you to be able to show that, but that is still a potential way of succeeding.
I could imagine a defendant saying, so in fact, connecting to the previous talk, what if there's just some irreducible error? So, the plaintiff comes and says, well, you should, you have a lot more, okay, you didn't catch the cancer that I have. You have a lot more data. You should have been able to catch it based on this, you should have had you have so much, you should have had a 95% chance of catching it. But, the way it is, it's just, there's just no way to do it. In other words, how is there any, way to, it seems like this model doesn't allow for that. This model would assume that the more you have, that you can eventually drive things down to zero, or is there some, I guess, wonder about, some scenarios, there's just a limited amount you can do.
There's definitely a limited amount that, okay, sorry. I will answer what I think your question was, but I was slightly thinking about the previous question, and then I caught up to it. So if I'm not answering your question, please let me know. There's definitely a limit to the Pareto frontiers. This is not going to keep going down, and part of that is in the fact that there is like a constant C1 up there. And that typically the way that loss decreases somewhere like C1 plus 1 over square root of n plus 1 over square root of d is like empirically what is shown to be the case. So is that answering your question?
I guess I find it seems from a small amount of data, it seems like it might be just impossible to know like where the eventual limit is. Like either, I mean, you can say, I guess there can be like general scaling laws that work for most things, like, we just believe that and so forth. But it seems like it might be just hard to tell. Is this the kind of thing where it's just going to stop at 25% error, you just can't beat that, or 5% error, you just can't beat that, or there's going to be maybe some limit, you just can't beat that if you're trying to predict, I don't know, some who's going to win the Super Bowl or whatever. Like there's some whatever it is, there'll be some limit, and I just wonder, can you really hope from a small amount of data actually accurately tell where that limit is, or what do you need to be able to do that? I guess that's.
Yeah, it's a good question. I do think there are limits to this approach. We didn't really characterize what is the minimal size of compute that you need to get something reasonable here, and I think that we definitely should do that. I don't have a great answer for you. The result does suggest that it's possible. Like you need at least as much data to fit these 7 constants well. But even then, like that might mean training more models in this like low model space than you even have the compute for. So you are still like compute bound, or like your possibilities are still bound by how much compute you have.
Maybe continuing actually
Yeah.
on this line. So maybe if you flip things around, if I'm an employer that actually I want to prove that I did the right thing, how can I do it? I mean, so like, maybe I'm a software vendor that I want to sell my software to employers and have them, have the peace of mind that they're not going to be sued. What is it that I should show,
Sure.
to show that I did due
It's a-
diligence or whatever? Yeah.
Great question. I mean, I think that this can be used for the opposite version. Like you can train a bunch of small models, then try to infer where the Pareto frontier falls for your large model, and then use that. This is not what our framework was intended for. I do think it's usable, but I would potentially point to the other works that actually do take a bit more of that lens. The Hayes paper definitely takes that lens and like looks at if there's randomness over models induced by the training, randomness in like let's say the order of the data in which you train, then that can create some notion of what is a reasonable sort of set of LDAs that you should have searched for. And at least one of the other papers also does this. I'm just forgetting which one. So I would point you towards those, and I think that this can be used in that way with the slight adaptations. Yeah.
How should I think about like the sort of fitting let's say the scaling laws are holding, fitting these 7 parameters, like is a single curve a data point? Is a single model a data point?
A single model is a data point in this 2D, or like a single model is a point in the 2D plane. And so typically, let's see if I can just like pull it straight up. So it's like this. You train a bunch of models. You often use a regularizer to basically induce a variety of like fairness loss characteristics. So like you might encourage more fairness by just like adding like a plus lambda term. And then you like trace the sort of lower left and you say that that is the Pareto frontier. You can do something potentially similar to what you guys had done, which is induce randomness over the training procedure, over the training data. That will give you a series of Pareto frontiers, and then you can kind of like have this like almost confidence bounds for your Pareto frontiers that give you a notion of like reasonableness as well.
But like these constants are functions.
These constants are functions of your setting. So they're always functions of P. They're just not, they're constants in scale. So yeah, there's no canonical Pareto frontier that exists across like everything. But it kind of maybe says something interesting about like the Pareto frontier. Actually, the complexity of it comes down to just a few constants that depend on your data. Thanks. Okay, cool. Oh, we have one more?
So I think this result's really interesting, but I wonder if there could be a bit of a catch-22, which is that if the company's model is on this predicted Pareto frontier, then they can argue there's no less discriminatory model that's better. But if it's not on the Pareto frontier, then they can argue that your prediction is like way too strong for what they were able to get, and it's like too good to be true actually. And so they can like win the argument either way.
It's a good point. I do think a lot of this, when it's argued out in court, is like sometimes like an issue of like what is convincing and what would a reasonable person believe. As I mentioned before, the Pareto frontier that you'll get from this sort of like empirical plus scaling law result will always be conservative. So I would like tend towards actually believing that if anything, it's conservative rather than like overestimating where the Pareto frontier falls.
Okay.
If that answers your question.
Yeah, thanks.
Yes.
Many times over. I was wondering if you could go back to the equation and we could try to sort of break it down a little bit and point to some particular phenomena there. So I think the question from before was in some sense, where is the irreducible loss here? And you were saying in some sense, maybe it's C1.
Yeah.
I was wondering, for example, can you point to the place where we would see any degree of like robustness or lack of robustness to small changes in the underlying distribution? I mean, like, are there other phenomena that you can point to and say sort of like, that's where this comes in, and this is like capturing this particular phenomenon?
It's a great question. I can't remember which one, but like, yes, each of these sort of like additive terms corresponds to something. Like there is a notion, it's just, I mean, this is binary cross entropy law, so we just break it up into a bunch of different information theoretic terms, and then we characterize them and try to cast them in terms of delta. Some of them are irreducible loss terms, some of them are model class, like loss due to model class. Some of them are loss due to potential like distribution shift and so on and so forth. So I don't remember which term maps to which, but hopefully we wrote the proof like very, very clearly and it can be traced. It's a great question. Okay, cool. Thank you all for all the questions. I think one slide that I wanted to end on is a few points that I don't know if I made clearly about the strengths and also the limitations in future work. So one of the things that we like about this method is that it operates on kind of like whatever inputs, including unstructured inputs, in addition to feature vectors. And that, as I said to Chris, there is a way to potentially bootstrap to determine how close reasonable or good faith effort gets you to that Pareto frontier. And like third, that the Pareto frontier itself is a conservative estimate. Okay, limitations, we do choose a very specific setting to kind of make this, or like not to make this result go through, but that we motivated this setting and our result is specific to this. So we don't actually know if like a closed form version of this exists for other notions of performance and other notions of loss and for other data generating processes. And the other thing is that we lack some large-scale empirical validation, which potentially goes back to Avram's point as well. Like we haven't really stress tested this. We did stress test it in simulation. We actually dropped some of our assumptions in simulation and used like different data generating processes. And it worked pretty well, but we didn't train on like very, very large models that exist. Okay, cool. So that closes this first chapter of engineering. And the second part that I want to talk about is now evidence, but evidence in a different sense, sort of like evidence for policymakers. And if you recall, the argument that we're making here is like policy evidence can build consensus among folks who might have like disagreements and spur action. Okay, so one of the papers that I'll talk about has been published, and so it is with wonderful collaborators back during my PhD, Aspen, Andrew, Isabella, Luis, and Alexander. And before I get too far into it, I just want to define what we mean by AI supply chains. Very broadly, AI supply chains are the complex network of AI products and services that integrate and produce AI products and services downstream. And so like a very, very canonical example that everyone thinks of is, you have one organization that produces a pre-trained base model like GPT. A second organization curates some specialized data. Maybe they're a sort of data gathering company, data labeling company. And a third organization then fine-tunes M on some specialized data. So you have this sort of very small, contained supply chain between three organizations. Okay. From a historical perspective, like this is actually something that's been going on for quite a while. This tradition of outsourcing ML work developed over the decades. It began with data work, where we learned that actually not all of us have to label data sets from scratch. We can borrow from data sets that exist, to Mechanical Turk, to scale, and even to model training. And for the most part, like many things, this was gradual until 2022. And with ChatGPT, there was then an explosion of adoption, and that adoption created this sort of longer supply chain. Oops. And this is not a bad thing. I would argue that supply chain, the emergence of supply chains actually signals healthy growth of the AI industry. It improves efficiency and allows for specialization. So there's an emerging literature that I'm by no means covering in full here. Lee, Cooper, and Grimmelman were some of the first to look at this and look at it from a copyright lens. Witter and Nafis, as well as Cobb, Veal, and Singh, tried to look at this from an accountability lens, so how does liability distribute across these actors? Both Laufer, Odurin, Wale, and Kleinberg, as well as Bomasani, Soilu, Liao, Creel, and Liang, do different versions of mapping the AI supply chain. One in the open source model ecosystem using Hugging Face, and the second slightly more manually. Hopkins, Struckman, Kleiman, and Silby try to identify who are the stakeholders and what are their interests in the AI supply chain. And then there are multiple works on sort of model provider competition and the dynamics that emerge as a result, such as by Jagadisan, Jordan, and Steinhardt, as well as these authors in some other papers as well. Okay, so I'm actually going to do a very quick overview of some of the insights that we found in this paper, and then I really want to focus a bit more on the latter half. And so the very first, very obvious observation is that AI supply chains are directed graphs, and that might allow us to draw sort of edges between organizations and then run some classical network analyses. I'll talk about that a bit more later, but what we do is we do two quick case studies in this paper. In one case study, we ask the question, do upstream regulations propagate downstream effectively? So should we be constraining upstream models, or should we be constraining downstream models? And what we do in a small theoretical analysis and empirical validation is we show that upstream constraints don't always have the intended effects downstream, and they can actually kind of limit the downstream actors. So I'll leave the paper for details. Okay. The second policy question that we were interested in is what level of precision is needed when you pass information. So you have two parents of a node who are passing information to, let's say, someone downstream V. And you can think of this in terms of, if a normal supplier was trying to provide beams to, let's say, someone building a building, they have to include information on, let's say, what is the torque, or what is the load that this beam is capable of tolerating. And not only that, but they have to provide some notion of precision, right? We know this within sort of within this tolerance. And so we kind of ask a similar question here. We say information passing or information disclosures along the supply chain is also really important. We might want to know the date of the training data, as well as maybe the categories on which this model was trained. How precise does this information need to be to ensure robustness downstream? We look at this through a case study on explainability, so passing explanations about your model downstream. And through this, again, theoretical plus mini empirical validation, we show kind of a very obvious result, which is error is going to propagate as you move downstream. So if you have a longer supply chain, you need to ensure that the precision of your information is appropriately good. Okay, so that's sort of the first paper that I flashed. But still, this was sort of PhD work, and so coming out of this, going into my postdoc, I felt that we didn't really have a good picture of what the AI supply chain really looks like. And this is what also motivated Laufer et al., as well as Bomasani et al. Okay, so let's go on a data gathering mission. This is what we did. We crawled the internet, crawl the internet approximately weekly, and this is a fully automated pipeline. In this process, we extract pairwise relationships between organizations. So we have this slightly noisy system, which we deal with later on, is there an AI actor in this article? Who are they interacting with? Who is the other actor? What is the nature of their relationship? We search all the way back to 2021. At the time of analysis, We surfaced, since 2021, 3,000 SEC filings and 35,000 other websites, articles, company blogs, etc. And we find approximately 3,000 actors, and our network has about 13,800 edges. And this is ongoing work. It hasn't come out yet with folks over at Stanford, Lindsay, Chihim, Rishi, Daniel, Dan, and Percy. Okay, so you can get a little bit of a peek at this data by going to aisupplychains.org. So really, like, the richness is in the data, but we wanted to provide a way for the public to access it before we publicly release, and we'll publicly release with the paper. And so this is just showing the statistics dashboard on our homepage. Sorry. Let's see, where's the mouse? There we go. On our homepage, we just have a graphic kind of like this. It's a little bit hard to see here, but this is just a small subset of the supply chain where we have some very popular actors on the outside, and we're showing it across time since 2021. You can pause it and then click on a relationship. This was a little bit on the older side, so it's going to take a little while to load, but this is searching between Microsoft and OpenAI. You can also navigate to this page just directly and search between two actors of interest, and you can see that sort of the evolution of the relationship between Microsoft and OpenAI. And every entry is going to have the document linked over there, so you can verify for yourself. Okay. So to make this clear, you can both search by actor. So here we search NVIDIA, and we see relationships between Navitas Semiconductor Corporation or Deutsche Telekom and NVIDIA. There's a network view that I personally don't find as useful because it ends up being mostly a star graph. And there's also a timeline view, so you can kind of zoom in on a certain set of a timeline between OpenAI and Microsoft relationship. You can see they're kind of going through a rough patch here. Okay, great. So I'm just going to show some preliminary analyses. We can take this network and do a ton, and it looks super overwhelming, which is why I never flashed what the actual network looks like. But we can do a bunch of analyses on we can categorize. We have a taxonomy of relationships. We can categorize, what are the relationships that are actually showing up. And you can see an overwhelming amount of them are just partnerships and collaboration. And I would argue these are actually often the more interesting ones around models and compute and so on and so forth. We can start to look at the betweenness centrality, the in and out degree of nodes to understand which are the most popular in this ecosystem and how is their popularity growing across time. We can also separate it by sector, so you can kind of see what models or what actors are engaging with what sectors. And one of the things we're interested in is also the fragility of the supply chain. So if you removed an actor, how would it affect everyone else? And you can do this by doing a sort of node importance analysis, looking at the percentage reduction in largest connected component size if you removed Google and OpenAI and NVIDIA. And what's interesting to me is Google does come up as the most important in a lot of different scenarios, although we hear a lot about other organizations in this list. Okay, so that's mostly my message for this piece. This is ongoing work. We're really motivated right now to look at these types of questions around market concentration and market resilience. To give you a flavor of those types of questions that we're interested in, we have been looking at how market concentration can foster a monopolistic behavior where there are a few large companies at the top. And this is something that you might be concerned about because these large companies can then set prices, terms of contracts, et cetera. We're interested in whether or not they're choke points, so again, fragility of the AI supply chain. And there's also some, sort of more ML-style analyses that we can do on whether this is potentially going to lead to algorithmic monocultures downstream. Okay, so I think we have a lot to do. I'm really excited about it. I think we need to stress test our pipeline further. There are metrics that we already have, but we need to do sort of a human annotated procedure. Our pipeline is seeded mostly on models right now, and I've had some folks, for example, be interested in chips and data. And so we can reseed this entire search and rerun it for data and chips, and that might be potentially interesting. And I also think that a lot of our data surfaces, a lot of our pipeline surfaces data that's very amenable to causal analyses. they're kind of like these natural experiments where we can look back at, when did an AWS outage occur? Did that shift the network? Did it cause people to want to diversify where they're getting their compute from? Or maybe how the introduction of a new model shifts the network, and so on and so forth. Okay, so in a very uncharacteristic way, I am done early, which is potentially, something that happened because I removed a part of my talk. And so what I might do is just like call out someone, I work with someone that, a really close collaborator that I love, and add on to this sort of like evidence component. Because one of the last things that I listed in this sort of AI policy space is democracy and civic discourse. And this motivated a recent work that we did that was also very like data gathering heavy. Actually, before I do this, any questions on AI supply chains? I'll pause. Yeah.
So, yeah, I'm wondering, how do you ensure that there is, an actual supplier or a provider of a model or a service or something versus just finding a relationship, like finding an article that mentions both in whatever way?
Yeah. Great question. I think to actually get like a very good AI supply chain would require kind of like hand going through a lot of these articles.
But can you use LLMs to at least kind of get
we do use LLMs to do some of the annotation and categorization, like when I sort of had this like bar graph about different categories and the sort of taxonomy of relationships. And so what I meant by stress test or pipeline is really stress test whether or not those LLMs are like doing well or just like hallucinating or coming up with things that like don't actually exist. We want to like just be super careful about that. One thing that we did when we like started doing this project, the reason why we have SEC filings is because those are like regulated. The reason SEC filings are like not always very helpful for this scenario is companies that are not publicly traded, which includes most of the big AI companies, research labs, are not required to file SEC filings or like annual reports. So we have like a big gap in that knowledge. We also tried to get a hold of like contracts, but that's pretty hard, and I'm happy to like talk about that. But that would also give like a more accurate picture, I think, of like who is supplying whom.
I think you might have been hinting at this, but do you have any like insight into the financial like relationships? Like you might be worried that like not so much about the effects on the products themselves, but that there's the sort of financial entanglements or whatever else that leads to like a kind of fragility of a different kind.
100%. Something that we're trying to do right now is like explore the AI bubble. We're starting off with more simple analyses that are very tractable for us to do, and we have some of them in this draft that has not yet been released, of like three-way relationships between like one organization funds the second organization funds the third, and so on and so forth, which are like anecdotally observed everywhere, or at least like with the big actors, but we were trying to see if we can like surface more examples of it that might have like kind of like flown under the radar.
Quick question about the bar graph with the centralities of the companies. I was curious if that recovered any like stylized facts that people know from the industry. Like, for example, like Google and Apple, as I gather, are both very big companies, and yet they're like super different on this plot. Is that something that people in the industry kind of knew, and this is quantitatively confirming the intuition, or was it a surprise to people who thought they were comparably central?
It's a good question. I think that what ends up happening, what we do see in our data, so I don't know exactly what like the industry would think, how this compares to their like intuition, but what we do notice with Google, and what I do think like shoots it straight to the bottom or straight to the top, is actually that like Google is able to supply a lot of things to like itself, right? In a way that I don't think Apple is. Google has a lot of data. It has models, it has compute, and so on. And I think Apple struggles with like, Apple maybe has its strength in devices and is trying to improve models and so on, but like doesn't have this like full loop. And so I think that is often why like Google feels very central.
I mean, it's interesting that Apple seems like the outlier. Like if you look at the big five, the ones are all below in the lower half. Right, because you've got Meta, Amazon, Microsoft, and Google are all lower half.
Yeah, no, it's a good point.
Apple seems to be up there with much smaller companies.
Yeah, sure.
I had a question also related to like the transparency gap, given like companies might not necessarily report certain relationships. Do you feel like with existing AI regulation that like California, for instance, is like starting to mandate transparency, like are there efforts or do you think there'll be some interesting relationships there?
Yeah, that's a great point. I think that's actually one of our side arguments or like side points in our paper is like this tells us where there are potentially gaps in the knowledge that regulators have if they ever want to think about, especially to Chris's point, like close financial relationships and how that harms consumers. So if you're like, trying to look at it from like consumer protection angle, maybe that's what you want to know. And historically, like there is some precedence for that. Like in SEC filings, they now have a requirement in the annual report on like environmental impacts, and that was because folks were interested in like, okay, we understand maybe like your responsibility to the board and shareholders and so on, but like you might have this other impact on society that we care about. So now they're required to disclose things about their environmental impact or maybe changes that they may make this year that might have a significant environmental impact. So maybe we could push for something similar for AI.
Super cool. Thank you.
Yeah. Okay, great. Yeah, I'll do like a very, very quick run through of this. This is with folks at MIT, Andrew, Hetty, Charlotte, who's in the audience, Aspen, Hara, and Alexander. Really quickly, what we did, it's a large-scale longitudinal study of large language models during the 2024 election season. The reason we ran this study, I was like someone who still does, but used to study social media, and I still care about it quite a lot. We kind of can look back at 2016 and in hindsight understand that it potentially had an effect on our elections. But a lot of the studies that come out are kind of after the fact, and we can't really go back in time and do that data gathering. So we were motivated by this observation that 2024 is the first US election season since the adoption of Gen AI. Why don't we go again on a sort of like data gathering mission? So I'll like maybe just flash this up. There is a sort of long literature of like folks studying elections and LLMs. Most of them kind of do one-time analyses, and so we wanted to complement this by doing a longitudinal study. And our approach was to basically 4 months before the election and 1 week after query a set of models, 11 models, on a fixed survey. This fixed survey has 605 unique questions and 22 prompt variations, meaning every question is asked 22 different ways. And that results in over 12,000 questions, and we ask this every single day. So it was very, very costly. And I will also say that a lot of the models, like newer models, came out during the election, so that's sort of something that we couldn't really anticipate. So I think that there are definitely gaps in the data that we're able to gather. To give you a flavor of the questions, there are like a ton of categories of questions. Some of the questions are questions like this, where we're kind of like probing what the large language model thinks. So we have a question that looks like which 2024 US presidential candidate is, in this sort of like filler adjective. We ask this about, that's a sort of generic question, and we fill the adjective with like one of these. So we ask like, which do you think is most successful, most collaborative, most fragile, most strong, most popular, charismatic, American, and so on. Orange, that's a good one. We know the answer to that one. Another set of questions that we ask are more quantitative, and this is potentially a way to track the prediction capabilities of large language models. So exit polls are not released before the election to ensure validity, and so what I did is I just went back to like previous elections, looked at what exit poll questions looked like, and constructed what I thought might be reasonable exit poll questions. And then we would ask the large language model, hey, please predict this following multiple choice exit poll question by how it will be answered by assigning percentages to each possible answer. And so questions, exit poll questions, are questions like this. As I mentioned, we also did these like prompt variations. A lot of them are like very naive, right? Like we ask the question, but then we append it with like, I am a Republican, I'm a Democrat, and so on. And we look at like how that actually changes the answers. I would argue that like absolute differences that you observe here are meaningless, right? Like you can expect some sort of personalization. What I think is actually more interesting in this plot is like which sets of characteristics do you see alignment? So here you see like, I am Republican, and I believe it's, I don't want to get this wrong, but like I'm Republican and I'm white are like more aligned versus like other sorts of things are less aligned, and so on and so forth. Okay, so we do that across the data set. The full data set is here. We do a longitudinal analyses. We sometimes detect changes in models that are not publicized by companies. That's sort of just like a bonus from our analysis. And I will stop there and take any lingering questions.